Could you all take your seats, please? It's a great honor to introduce the 2017 Lecar Prize Lecture. This annual event was established by a gift from the estate of Myron Mike Lecar. Mike was an astrophysicist at SAO for more than 40 years, as many of you know. He came to SAO at the invitation of Fred Whipple. And his work ranged from the use of Vanguard 1 during his time in the Navy to make one of the earliest measurements of the J2 of the Earth. His work ranged from that through cosmology and then on to the study of solar system chaos, planet formation, and exoplanets. Mike was particularly proud of his role in establishing the first observatory in Israel, the WISE Observatory. He was also a founding member of the Origins of Life initiative, which, along with Dimitar Sasolov, which had his major meeting this week. Mike was a very generative character with many friends and colleagues. He taught a lot of Harvard freshman seminars on a range of topics and lured many students who thought they would become doctors, physicians, into becoming astronomers. He nurtured careers, spawned collaborations, and mediated disputes. But Mike really loved exoplanets, and he played a role in ensuring that the CFA became a major center of exoplanet research, long before we said exoplanets, when we said extrasolar planets. So it's very fitting that we would award the Lecar Prize to Dr. Natalie Battaglia, and we're honored to have her here. Natalie is now the project scientist for the Kepler Mission. You've heard of Kepler, right? She's worked for Kepler on the Kepler Mission for 17 years, right? So, and we concluded that we're, started graduate school, ended undergraduate, started graduate school about the same time. So she's basically dedicated her full career to Kepler. The scientific success for missions like Kepler is the direct result of the vision, creativity, persistence, and leadership of people like Natalie Battaglia. She's one of a very rare group of people. She's not only a gifted scientist, but she's also able to marshal the talents of a diverse group of engineers, scientists, and managers toward the kind of phenomenal success that Kepler represents. So we are thrilled to be able to recognize Dr. Battaglia's contributions to exoplanet science by awarding her the 2017 Lecar Prize. And so, Exoplanet Prize, that would be great. So with that, I present to you Natalie Battaglia.
Thank you very much. How's the sound? Is it okay? It's a great honor to be recognized. It's an honor for the person that Mike Lecar was and his advocacy for exoplanet research, but also for my dear colleagues here at CFA who have really shared this journey with me over the years. A shout out especially to Dave Latham, who's been a tremendous source of support since day one. As Matt said, Kepler has been my entire career, but I'm old enough that I started out as a stellar astrophysicist, like many of the people who do exoplanet research today. But I've also been in the really unique position of being able to see the careers that Kepler formed. Courtney Dressing, for example, who was a graduate student here at Harvard, probably was in high school when Kepler launched. And I saw her enter as a young student, write her thesis on Kepler data, and now soon she'll be joining the faculty at UC Berkeley. So to have that kind of perspective and see careers formed like that has been a great honor. So this award is also kind of embarrassing in a way, because projects like this don't happen without the efforts of hundreds of people. And so in this lecture, I hope to pay forward some of this honor to the people that have contributed. What I'd like to do is give you a sense of what Kepler has been doing over the last couple of years as we round the corner and head toward the finish line of the Kepler closeout. So you'll hear about Kepler closeout because in this year, 2017, in September, at the end of the fiscal year, the Kepler Prime mission will turn off the lights and go home. The spacecraft itself is still flying under the K2 extended mission and will operate for at least another year after the Kepler Prime closeout, so not to confuse you about the distinction. The science I will be talking about will be the science based on that first 4 years of data where we stared at the Cygnus Lyra region of the sky, unblinkingly for 4 years with the express goal of determining the fraction of stars that harbor potentially habitable Earth-sized planets. Right? So I am going to get into the nuts and bolts of what we're doing because I want you all to leave with a sense of how much work has gone into leaving this legacy of data products, which I expect will be studied vigorously for a decade at least in the future. Right? So I've already said some of this, but here's kind of a timeline of, history since just launch. Kepler was actually selected in 2001. I arrived at Ames in early 2000 and helped with the writing of the proposal. It was selected in 2001, but not launched until 2009. So the green colors mark celebratory moments like the launch in 2009. We stared at Cygnus for that first 4 years, and almost 4 years to the date. Right after, in fact, we got word from NASA that we had won an extended mission. And in fact, it was on my birthday that day. As I was about to take a bite of my birthday lunch, we get a phone call that said Kepler had lost its second reaction wheel. So that happened in May of 2013. Reaction wheel number 4 failed. And we went back to the drawing board, and the engineers figured out a way to keep Kepler flying using solar radiation pressure to balance the third axis of rotation that keeps the pointing stability. And so Kepler continued, and now it's actually it will have doubled its lifetime when all is said and done, with the caveat that it can no longer observe the Cygnus Lyra region, which is what we had proposed to do in the extended mission. But it kind of forced our hand. We had to actually repurpose into and turn into an ecliptic mission. And I'll say more about that in a second. So let's see, some other milestones in purple. The numbers that you see are the various catalog deliveries of exoplanet candidates from 400 to 1235 to 2336, and really we did not expect there to be such large numbers, owing primarily to the fact that we have these compact, very coplanar planetary architectures that we didn't expect. So we had tremendous numbers, and when all is said and done, we are reaching into the 4,000s. And so we will be delivering our final catalog. Actually, we kind of did it on the low about 2 weeks ago. We have a preliminary version of our planet catalog already at the NASA Exoplanet Archive, and I'm going to give you a preview of it today. So that's going to be called our DR25, Data Release 25 catalog, and that will be our final planet catalog. All right. So as I said, K2 was repurposed as an ecliptic mission. Kepler stared at 100 square degrees in the region of Cygnus Lyra for 4 years, almost to the day. In doing so, surveyed about 0.25% of the sky. So we were looking deep, looking faint, going out 3,000 light years in order to do a demographic survey of exoplanet populations. Then we had to make use of solar radiation pressure to balance pointing after the loss of the reaction wheel, and Kepler turned into an ecliptic surveyor. So think of the purple cones as more of a torus coming out of the board. We are surveying the ecliptic, and in doing so, when all is said and done, we will have surveyed 4% of the sky. So that has really changed the astrophysics that's getting done. And that would be a whole nother talk, so I'm not going to get to cover that today. But I will point out just some of the comparisons between the two. First of all, you might think that using solar radiation pressure to balance pointing might not be such a good idea. But it turns out that the photometric precision we're achieving with K2 in this mode is actually comparable to the photometric precision we received with the Kepler baseline mission. We're getting about 30 part per million photometric precision over a 6-hour period for a 12th magnitude star. And with Kepler, we were getting between 20 and 25. So we're doing very well, and it's enabled a lot of science. And this fellow, Jeff Van Cleve, is the person who repurposed the Kepler pipeline to deal with some of the other systematics by way of this reaction wheel loss that we had. In terms of the populations, here's a kind of a proxy HR diagram of stars of K2 on the left versus Kepler on the right, plotting the solar radius versus effective temperature. And it shows the distribution of stars, the star populations that are observed. And this is just to make one singular point, which is that Kepler wanted to determine the frequency of potentially habitable planets around G-type stars, solar analogs. Whereas for K2, because now we have access to so much more of the sky, the objective is primarily to survey the nearby populations, and that's weighted towards M dwarfs. So you can see that the mode of the distribution in these two cases is quite different. And this is Dan Huber, who's, I think, screaming, "Gaia, please!" And he's been in charge of the working group who generates the stellar properties catalogs for Kepler and K2. Okay, so the name of the game for Kepler is to use transit photometry to find planets. Here's an example of a multi-planet system, Kepler 11, with its 6 planets, and its nice sequence of folded transits that you see here on the right, from the innermost planets with their short duration, all the way out to the outermost planets with their longer duration, reflecting Keplerian motion. Very beautiful. This is from Jack Lissauer's paper. So the last time I gave a colloquium here was in 2011. Actually, I looked it up. And this was the plot that I showed in 2011, or a version of it. And this is what the Kepler catalog looked like back then. There were 1,235 planet candidates represented by the yellow points. You've got the pink points, which are the ground-based transit survey. In fact, it's not quite fair because those are the pink points as of today. And then the blue points, which are the Doppler velocity detections, also as of today. But this was the second catalog that Kepler released, and it was the paper itself was led by Bill Barucki. And here's a picture of Bill, the PI of the mission, leaving NASA Ames for the last time on the day of his retirement. So his very last work day at NASA Ames. Now, I'm going to show you what the catalog looks like today as of this preliminary version of the DR25 catalog. So this is it. There were 8,054 transit-like events that were identified by the pipeline, and that translated to 4,034 planet candidates. 3,789 of them, I would say, are very, very ultra-high reliability, greater than 90%, or actually probably more like 95% and higher. And of those, 2,331 have been confirmed by ground-based follow-up, by additional follow-up analysis of Kepler data itself, by statistical validation, many of them by people in this audience. Susan Thompson is leading this effort to generate this final catalog. She's doing an amazing job. She's going to be leaving us soon to head out to the Space Telescope Science Institute to work on their archive in preparation for JWST. Okay, so now I want to get into the nuts and bolts of how this catalog is presented. I gave you the money shot at the beginning. Now I'm going to circle back and dive down into the details. The Kepler pipeline uses a matched filter to find signals in an automated fashion, right? For this final catalog, we had instituted a lot of improvements to really achieve higher sensitivity as we try to dig down deep to get the lowest SNR transits of Earth-like planets in the habitable zone. And so we opened up the floodgates and had higher sensitivity in order to make sure that we examined everything that the pipeline thought could potentially be a planet candidate. And so this is what the histogram, the distribution in orbital period of those events looks like. And I'm comparing the DR25 new catalog with the DR24 old catalog, okay? The previous catalog. And in this DR25 catalog, we had 34,000 events that we had to look at, periodic transit sequences that we had to look at. Compared to only 20,000 previously. And again, this is owing to higher sensitivity and also relaxing a little bit of the rules that let things through. But in this period histogram, you can see a lot of anomalous features, right? We don't expect real planets or even real eclipsing binaries to have any sharp features in this period distribution. You expect for the physicality of the universe to be rather smooth. And indeed, if you look at these kinds of features, you see interesting things like, for example, RR Lyrae and V380 Cygni, two very bright stars in the field of view, are producing anomalous ghost signals elsewhere on the focal plane. So they produce this overabundance of transit-like signals. We also have a spike here due to quarterly gaps in the data due to telemetering down, turning the spacecraft and sending the data back down to Earth. It causes a shift in temperature, and that generates some spurious TCEs. TCE stands for threshold crossing events. So these are the transit that come out of the pipeline. But we also have this spike at 372 days, which is the orbital period of the spacecraft itself around the sun. Okay? That's producing a lot of anomalous signals, which is terrible, because what we're trying to find are Earth-Sun analogs, right, which have an orbital period of 365 days. So this is going to wreak havoc with our small planet candidates in the habitable zone around G-type stars. Moreover, there's a bump there, a spread out bump, and that bump is due to something we call rolling band artifacts. This is an electronic signal on the focal plane that is temperature sensitive. So the temperature changes a little, and this pattern, this electronic pattern, which we call, it's like a moire pattern, it starts to drift if there are temperature changes. And so it drifts across pixels and ends up looking like a transit. Well, the stars themselves rotate to different electronic channels once each quarter. So that's actually good, because it's not on, a star is not on a bad channel all the time. But it means that once a quarter it is. So these anomalous rolling band signals can actually beat at an orbital period comparable to 365 days, right? So this was another issue. Okay, Joe Twicken is the one that did all of this hard work to tune this process of detecting the raw signals in the data, and has a paper that describes those results. Now, every time you do a survey and you want to do population studies, you have to quantify the survey reliability and completeness, okay? Two very important measurements to debias your sample. So what we do for completeness is transit injection. At the front end, at the pixel level, we inject fake transits and we propagate them through the entire pipeline. Jesse Christensen, who once upon a time, I think was a postdoc here, and is now at the NASA Exoplanet Science Institute, was responsible for the pixel level transit injection. And here's a radius orbital period diagram that shows all of the injections that were put into the front end of the pipeline. And this allows us to quantify our completeness. You can see that the distribution is not uniform, and that's because above about 3 Earth radius, the completeness is just about 100%. We don't want to waste our injections probing or quantifying the flat part of the completeness contour, right? We really want to probe carefully where the completeness is changing dramatically. So that's why we focused our efforts in that part of the diagram. Now, reliability, that's trickier, right? You don't have ground truth to say what's actually a planet and what's not. So how are you going to quantify reliability? Well, we came up with the idea about 2 years ago of taking the data, the flux time series, and multiplying them by -1, inverting them. So transit pulses are no longer going to be detected, right? But these rolling band artifacts are actually symmetric upon inversion. So you'll still detect those. The only trick then is to be able to identify astrophysical signals that might also be symmetric upon inversion that don't get filtered out well. Most of the astrophysical signals get filtered out by our wavelet analysis and our detrending algorithms, our harmonic removal filters, etc. Some of them produce residuals. So we went to a great deal of trouble to identify what those astrophysical confounding signals might be. We filtered them out of the data, and then we inverted the data. And when you do this, you can run that inverted data through the pipeline. And on the top, here's this same period histogram. On the top, you have the histogram of the normal events that I showed you before with that 372-day spike, etc. And then just kind of flipped so you can see the comparison is the same for the inverted data. And you can see that they mirror one another quite well. The only caveat is that on the top, we actually removed the astrophysical, the transits, the actual planet candidates and the known eclipsing binaries, so that you could compare apples to apples, right? So this diagram made us think, okay, this might actually work, all right? And so we went down this road once we saw this diagram of using the inverted data to characterize reliability. And I'll talk a little bit more about that. Okay, so once the data comes out of the pipeline, now you've got a bunch of things that look like transits, but we already know that nature can fool us because there are astrophysical signals in nature that mimic planet transits. Eclipsing binaries, be they in triple systems or in a background like behind in the photometric aperture confounding you. There are a multitude of astrophysical signals that can confound us. And so over the years, we have devised statistical metrics based on Kepler data alone to try and weed out the true signals from the imposters. When we launched in 2009, we did not have these metrics. We did not have a pipeline to do this vetting at all. We were cold turkey, mostly evaluating signals by eye. This is a very complex process that has evolved over the years and has finally gotten to a point in the last year and a half or so that it can be written up as a decision tree algorithm, which we call the robo-vetter. And Jeff Coughlin is the mastermind behind the robo-vetter. Doesn't matter what these words are in this flowchart. Suffice to say that the robo-vetter is making decisions to disposition these signals into groups of planet candidates, astrophysical false positives, or false alarms based on approximately 36 independent tests and literally hundreds of metrics that come out of the pipeline. This is a very well-tuned machine. However, when we applied the DR24 robo-vetter to the DR25 catalog, it didn't do so well. So here is a contour, well, a 3D a surface histogram of the transit events that came out as planet candidates, okay? And it's plotted as signal to noise on the y-axis versus orbital period logarithmic on the x-axis. And so you see this nice distribution of planet candidates, and you've got marginalized histograms on both axes. This one that's marginalized over period shows the distribution as a function of the signal-to-noise ratio. And you see the new catalog compared to the old has this nice excess of low signal-to-noise ratio events. But most of them are due to this bright spot here, which we don't like. But we do expect to have some here just because the Kepler pipeline itself has greater sensitivity now. So we do expect new candidates at lower signal-to-noise ratios. But you can see up there in the other marginalized histogram that you have that nasty 372-day spike, which we didn't have so much in our DR24 catalog. So we have to deal with that. So keep this in mind, this figure, what that looks like. Just to drive this point home, I have a quiz for you. Here's some actual plots that come out of our vetting suite. Just diagnostic plots that humans can actually look at. And I'm going to show you two, and your job is to figure out which is the real planet. Okay? So here's one. This is one of our T-cert vetting forms. On the very top, you've got the raw light curve, nicely detrended. So you see this nice Gaussian noise. It's been decolored. The noise has been decolored. The triangles denote where the transits actually occur. And then you've got some folded light curves, and here in the middle is the folded light curve zoomed in. And you see an object that's 1.3 times the radius of the Earth at a 252-day orbital period. There's no secondary that's visible. We check odd versus even numbered transits. Everything looks pretty good. It has a signal-to-noise ratio of 8.2. Looks pretty good. And here's the other. Again, a very nice transit, comparable orbital period, 200 and some odd days, radius of about, well, this one's a little bit larger, nice and deep. Signal-to-noise ratio is about 8. So everything looks good in both of these cases. A human being with all of our, well, the diagnostics that we had at the time could not distinguish these. These will both look like real transits. So one of them is real, one of them is not. Care to guess? The first one is real? Yeah? Second one is real? Okay, point made, right? Well, the first one is an injected planet candidate. The second one is from inversion. So the second one is not real. Okay, so we had to go back to the drawing board, and so the team devised a suite of new metrics. And what distinguished these new metrics from the old metrics is that they operated not just on the flux light curve itself and the centroids. If you're familiar with how we play this game, we also monitor the photocenter spatially on the CCD in a relative or differential sense. The new metrics had to really look at different diagnostics, like the period distribution, looking for unphysical spikes, right? Like looking at spatial distribution of these events over the focal plane and looking for bad channels. And so I've circled some key words. Look at each transit. Instead of looking at the phase folded light curve, look at each individual transit and see where transits might be running amok. Study the exact epoch of things and see if there are epochs at which you have a lot of false alarms or an anomalous number of transits. Look at the shape of the transits. Make sure that they are actually more correlated with a transit shape than they are, for example, a discontinuity in the data, which is something that we have called sudden pixel sensitivity dropouts that cause a discontinuity and a ramp back up. But they kind of look like transits. So we correlate our transits with those kinds of signals. All right. Here's an example. Here's the focal plane, and it shows in light gray dots all of the different TCEs. Okay, and the colored dots. They all of these dots correspond to a signal detection on the focal plane. But the point here is and so the colors represent different kinds of signals. But the point here is that you have overpopulations, right? You don't expect there to be more planets in nature at that exact point in the galaxy, right? So that's due to a bad channel. And so then you can take this and you can say, all right, let me look at the statistics. Here's all the different times where transits happen. And here are some spikes. And I can use this data to build up statistics. What is the likelihood of having a transit event at a certain epoch? And you can identify places where there's an overpopulation. And if that corresponds to one of these bad channels, then you flag that transit as likely being bad. Just from a statistical argument. There's nothing really against it except that all of these things corroborate. Okay? So you flag the transit as being bad, and that means that planet candidate has to stand on its own 2 feet with all the other transits only. Okay? All right. And so we implement these new metrics, and almost all of these artifacts are removed. Okay? And elsewhere, the distribution looks pretty much like last catalog. So that's pretty good. It does a pretty good job of removing those false alarms. All right? And so now, because we have injection and we have the inversion, we can quantify the completeness and reliability of this process, of this vetting process. And so here I have on the x-axis, MES is the signal-to-noise ratio of a planet transit. Here is the orbital period. And the box I'm most interested in is this one on the lower right, because that's the long orbital period, low signal-to-noise ratio transits that are most likely to be the small habitable zone planets around G-type stars. Okay? And so with this, I'm getting 76.6% reliability and 52% completeness. So that means I'm throwing away about 48% of the real transits, and I measure that from injection, just with my vetting rules. Throwing away about 50%, and I'm about 76.6% reliable. So it's okay, right? So at that point, we decided to look at all of these vetting metrics and ask ourselves the question, well, how clear-cut is it? We have a statistic that we're using to put things in one drawer or another. Planet candidate, false alarm, right? But is it like near the middle, or is it way over here, way over there? And we've got 36 independent tests, right? So what we did is we associated an uncertainty for every measurement that we make. All of these vetting metrics, we have a number, and we test to see if it passes a certain threshold. But now we attach an uncertainty to it, and we do a Monte Carlo to build up a distribution. Okay? And we ask ourselves the question, how frequently would this planet candidate be on the left side of the threshold? In which case we would toss it out, right? So if my measurement for a particular metric is kind of right at threshold, then it's about 50% of the time I would throw it out, right? But I don't have just one metric. I have 36 different tests, right? So I've got a sequence of these probability distribution functions, all with their own thresholds and all with their own probabilities. And so if just one of them fails in a given trial, we would throw it out. We would say it's a false alarm, right? So in this case, in this very simplified example with two metrics, you know, there's like 4 different things that can happen in my Monte Carlo. A pass-pass, a pass-fail, fail-pass, or fail-fail. And it only gets classified as a planet candidate 25% of the time, right? So the score would be 0.25 for this particular simplified case. In fact, I have 36 tests, and it's much more complicated, so you can end up with something that has a score that's near 0, but actually still be a confirmed planet, and you have to take that into consideration. But the score values have turned out to be very helpful for identifying the true high reliability sample. Okay? And so this is what it looks like. So here again is my period radius diagram. Now it's colored by this score value. So here it is on the left, the sample from the vetting metrics that I just showed you, right? And you can see that the very bad, those that have the very low scores, are kind of all at this 372-day orbital period. So now all I have to do is filter on the score value, and I can end up getting a very, very clean sample of planet candidates, okay? But how is that going to affect my completeness? Am I throwing the baby out with the bathwater? Am I still going to have something left over to do occurrence rate calculations with? Oh, let's see what it looks like. First of all, here's this plot again. You can see that it's very clean. And here's my completeness and reliability. Completeness was hardly degraded at all. I'm still at about 50%. Reliability is now at 93.4%, which we were just jumping up and down over. This, to me, was a great triumph. So now we have a very high reliability sample. And using that sample, where we've only got 50% completeness, or less than 50% completeness, let me show you what's left over in the habitable zone. This is the plot of the habitable zone planet candidates in 2013. In 2011, when I came here last, it would have been even fewer. We had next to no planet candidates in the habitable zone. So here I've got the energy received by the planet. On the y-axis, I have the surface temperature of the host star. So the orange dots on the top are Venus, Earth, and Mars. The green hatched region is the habitable zone, optimistic and conservative. The blue dots are the ones that are in that zone, and the size of the symbol is scaled relative to Earth. If it has a yellow number in the middle, that means that that planet has been statistically validated with very, very high likelihood that the planet interpretation is the right one, greater than 99%. So that's what it looked like in 2013, and here's what it looks like now. And that might not look like much, but when Kepler was designed and built, we did planet yield estimates that said if every star we observe has one planet, Earth-sized planet, in the habitable zone, we would expect to find about 3 dozen. Okay, so that means if the occurrence rate of planets is 100%, we should find about 3 dozen. Well, we found about 3 dozen. And the occurrence rate is not 100%. And this discrepancy, this overachievement, is not because we over-engineered. It's because 4 quarters into the mission, we actually changed the target list with the knowledge that we could go deeper and fainter. And we pushed from 14th magnitude down to 16th magnitude in order to capture more nearby M-type stars. And so now we've got a sizable population of small planets orbiting M-type stars, which gives us a very robust measure of Eta Earth, especially for the M-type stars. But with this very high reliability sample, we will be able to get a measure of Eta Earth for the G-type stars. Okay. What I've described so far is the completeness and reliability of that vetting step, where you're trying to put things into different drawers of planet candidate versus false alarm. Let me back up a little bit and say, well, what is our detection efficiency just going through the pipeline and through that transit detection machinery of finding these signals to begin with, those 34,000 things that we examined, right? How efficient are we at picking them all up? Well, we can do that with a pixel injection as well that Jesse Christensen started and others have actually improved upon. And this is what we get. So this is a plot of the fraction of signals recovered as a function of the expected signal-to-noise ratio. Okay? We have a detection threshold cutoff of 7.1 sigma that we've had since the beginning of this mission. If you have perfect, normally distributed noise, you would expect to detect 50%. 50% of the time, a planet candidate is going to, that has an expected signal-to-noise ratio of 7.1. 50% of the time, it'll fall at that or higher. 50% of the time, it'll fall that or lower. So you should, under best circumstance, have 50% detection efficiency at exactly your detection threshold, which is 7.1. All right? And so that is represented by the normal error function, the red error function. You can see that we don't do that well, but this is a significant improvement over previous pipeline releases. We actually do really well. It's almost very close to perfect Gaussian behavior. But we can measure it, and that's what Jessie did with a pixel injection. And she fits that histogram with a gamma cumulative distribution function. Okay? But this distribution is averaged. It's marginalized over all stars, F, G, K, M. It's marginalized over all orbital periods. It's marginalized over all impact parameters of your transits, whether they transit the center of the star or the limb of the star. So there's a lot of averaging there that goes on. And what people were interested in was, are there any star-to-star dependencies we should worry about? Because there's this result I'll share here in a second that says that M-dwarfs seem to make small planets more efficiently than G-type stars. Is that real, or is that a star-to-star dependence is the big question. And we were seeing star-to-star differences. So here are 2 examples of these detection efficiency curves, and you see significant degradation over here. And how much degradation you get seems to be correlated with the color of the stellar noise. Okay? So that was something that we were very worried about, and here's Joe Catanzarite from JPL who's been working on this problem. Chris Burke is a very notable name I want to say over and over again, because he's probably the person who has the most intimate knowledge of the Kepler data from the pipeline all the way through the transit detection and through the injection and recovery and the completeness part. He's an extremely valuable member of our team. And he started thinking about this problem, and he thought a lot about the marginalization over impact parameter. And so here's a theoretical diagram of how the signal-to-noise ratio should degrade as you go from a central transit that goes right across the center of the stellar disk all the way up to a limb transit, right? Where you've got you're just nicking the top of the star, right? You've got limb darkening, so you've got lower contrast, and you've got a short duration. And here are modeled transits as a function of limb darkening, or I'm sorry, as a function of limb angle, impact parameter. So this would be a central transit, and this would be a limb transit, okay? So you expect the signal-to-noise ratio to degrade in this very predictable manner, right? The problem is, when you measure it empirically, yes, some stars do behave in that way, but other stars are just really lousy. They don't. So if you're going to marginalize over impact parameter, you have to take what you would expect at the central transit and degrade it by a certain factor. But that factor is not analytically predictable. It depends also on the color of the noise for a given star. So this was something that had to be modeled. And Chris Burke looked at this very carefully and took the distribution of these signal-to-noise ratio measurements, these empirical measurements through the transit injection process for a given star, and he modeled that distribution as a beta function, parameterizing it with two properties that are well correlated with the noise properties of a given star. So if you know those noise properties, you can back out or interpolate from a table what the coefficients of the beta function are in order to give you a function that you can cross-correlate with or use as a weighting function. Not cross-correlate, use as a weighting function. Okay? So this is one correction that helped significantly with these star-to-star dependencies. He also found that there is a stellar radius bias. So here's that same detection efficiency curve, but now colored by the radius of the star. And again, this is well correlated with the noise properties. We have different ways that we measure the noise properties. I won't go into that detail. But he was able to regress on them and compute a model for how to correct for them. And this is going to be tremendously important for determining the occurrence rate around M-type stars, which are these degraded. You can see that they have degraded completeness, okay? Which, of course, is actually going to work to augment the occurrence rates, right? Okay, so here's what his models look like. Here's a completeness contour over this radius and orbital period space. This is an empirical or measured contour. What he did was he selected about 32,000 stars. He did intense transit injection on each of these stars over covering all the period and radius space using the NASA supercomputers, and he used those to model or regress out this behavior. This is the modeled contour, and you can see that there's very good agreement between the two. So now we have a star-by-star completeness model that we can use for our occurrence rate calculations. Okay, so that's the highly technical stuff. I'd like to end just by talking about a couple of science highlights. There hasn't yet been science done using these improved products because we haven't finished delivering them yet. They'll all be delivered by June, and they'll be available at the NASA Exoplanet archive. But a multitude of occurrence rate studies have been performed using previous deliveries, and I'd like to point out a couple of highlights, including one that was just released this week. The first is the radius distribution. This is what the discovery sample looks like in terms of a radius distribution if you correct for these biases and you look at the occurrence rates themselves. And the bars are colored by things that are expected to be mostly terrestrial, things that are expected to be mostly giants. They're kind of Neptune-sized and larger. And this literal gray area in between that we're kind of perplexed about. We don't really understand because we don't have any analogs in our own solar system. Whether or not this turnover in the occurrence rates is real is kind of open for debate, because I don't think our previous catalog deliveries really pinned down the completeness for these tiny, tiny signals at the very low signal-to-noise ratios. So I would take those with a grain of salt. But certainly we can say that small planets orbiting within 1 AU of their host stars are about an order of magnitude more common than giants. We can also say, if I sum the occurrence of all of these different size categories, that every star has at least one planet, because that number sums to more than one. There's a tantalizing dip here you might want to take note of. I'll show you that in a second. There seems to be a temperature dependence. So this is work by Heiss-Mulders, looking at the occurrence rate distribution now as a function of the semi-major axis for F, G, Ks, and Ms. And you see that the M stars systematically have a higher occurrence rate. But this is marginalized over small planet sizes. So this M stars, it seems, harbor more planets within 1 AU than their larger star counterpoints. Courtney Dressing and Charbonneau here at CFA. Courtney did this work as part of her dissertation, looking at this Eta Earth value for the M dwarfs. And when she looks at this habitable zone over here and does her bias corrections, she tells us that the occurrence of 1 to 1.4 Earth radius planets in the habitable zone of M-type stars is about 0.24. Right? Which means that the nearest potentially habitable planet is likely to be very nearby, within 5 parsecs. Chris Burke, again, led our own project occurrence rate paper in the last catalog release. And our objective for this catalog paper was not so much to iron or to think about the science, but it was really to understand the systematic errors. Where are the tallest poles? So for example, here is a posterior distribution for one occurrence rate measurement for 1 to 2 Earth radius planets orbiting between 50 and 200 day orbital periods. And you can see that the mode here is about 0.3 something, and you get an idea of its uncertainties. And then you tweak the knobs. You say, well, what if I use a different catalog for the star properties? What if I use a different completeness model or different input assumptions? And you start varying all of these parameters, and you get all of these other probability distribution functions or these other posteriors. And what this is telling us, or what it was telling us, is that systematic errors are dominating, right? They're more important than the width of that posterior, right? And so, but the value of that was that we could identify exactly what needed work, what were the tallest tent poles, and we could tackle them. And that's exactly what we've been doing over the last 2 years, and what Chris has done so brilliantly. Okay, and finally, before I pause and take questions, I wanted to show this paper that came out this week. This is Benjamin Fulton et al. Put this out on the archive, I think it was Monday or maybe last Friday. And so what they did, Jeff Marcy's group and John Johnson's group, and he was at Caltech back then, when Kepler first launched, we decided right out the gate that probably more important than doing high precision radial velocity work on these planet candidates was to go and get a spectrum to well characterize the host stars that they orbit. Because you only know the planet as well as you know the host star, right? So over the years, between 2009 and 2017, they used the Keck telescope to take spectra of stars, all the planet host stars, brighter than, I think, 14.7 magnitudes. Thousands of stars were observed. And that whole data set that they've amassed has finally been analyzed. They have updated star properties, okay? So on the left here, I have, again, the radius period diagram, and every point that you see is a planet host star. I'm sorry, it's a planet, okay? And you see that it's pretty uniformly distributed over this space. That was with not the last catalog, but the one before that. Now they've updated the star properties, which means they've updated the planet properties, and now the distribution looks like this. It's bimodal. These points have separated. So you take those updated properties and now you compute the occurrence rates. What does that radius distribution look like now? Looks like that. There's a gap. Remember I showed you in that previous radius diagram there's a tiny hint of a gap, but nothing we would ever believe, although in hindsight that tiny little difference has appeared every time we did the radius distribution for every single catalog. So what I think is happening is that those big uncertainties in the star properties were just smoothing out this distribution. And so now, here's Benjamin B.J. Fulton, a graduate student at the University of Hawaii with, maybe he's moved now, I'm not sure, now that Andrew's at Caltech. So we're calling this the Fulton gap. And the idea is that at a certain core size, you have volatile accretion that keeps planets large. And over on the left side of the gap, you have the rocky cores. And I'd like to circle back now to my period radius diagram that I showed at the very beginning. I didn't talk about it then, but in this period radius diagram, there are some interesting patterns that we've observed for a very long time. Namely, or primarily, that there's this triangle here on the left that has just been devoid of planets since day one. And this is a part of parameter space that's very well understood. We have very high completeness there, right? We also know from Kepler data that planets are moving around. We see all these architectures, systems that are in resonances. We see evidence that things are moving around, and that means that they can take their volatiles and carry them into the interplanetary systems. And so this triangle, it's been surmised by many theoretical studies, that if you have a planet that's down here, and it migrates inward and tries to cross that line, the surface gravity is going to be low enough that it photoevaporates. It basically loses its envelope, and that planet is going to decrease its radius. It's going to shrink when it loses its envelope. If it's above that apex, like the hot Jupiters, they migrate in, and they have a higher surface gravity, and so they retain their envelopes, and they just inflate. So they actually get bigger. And so something coming in and trying to cross that gap would just move up. Now we have a new bifurcation, which is this one here in cyan or light blue, which perhaps is due to volatile accretion. A planet that is near this boundary will have just enough core mass that it might accrete on hydrogen helium and thereby have a big jump in its radius. And then these down here will not do so and retain their just a rocky core. But you can see that the picture that's forming is very complex. We have to think not just in terms of period and radius, we also have to think in terms of that third dimension, which is their evolutionary history and how much radiation they're receiving from their parent star over that time and for how long. It's a very complex story that's building up, but Kepler is affording us, through this statistical sample of planets within 1 AU, affording us a complete picture of that planet formation history. So, just some concluding remarks. The final catalog and the occurrence rate products will be finalized by June and archived in NASA's Exoplanet archive. Kepler has produced a statistically significant sample of high reliability planet candidates suitable for exoplanet population studies within 1 AU. Small planets are 5 to 10 times more common than giants in these interplanetary systems. And I would say things are just now getting interesting. Now we've got the measurements, we've got a legacy we can be proud of that we're leaving into the archive. And I hope that scientists will start to write proposals like crazy to make use of that legacy. And finally, I've heard people say in public forums quite frequently, actually, that Kepler is not going to be able to weigh in on Eta Earth for the G-type stars. And I hope I've convinced you that that's not true. I do think we will yield an Eta Earth for G-type stars, especially once the Gaia data is released. Next April, in April of 2018, we get data release number 2. And then we will have parallaxes for every single Kepler host star and very accurate star properties, which should reveal additional detail in these occurrence rate distributions. So finally, just to say, I don't know, we're passing the baton. We're closing out this year, and I'm just really proud of the legacy that we're leaving, and I'm really excited for what is coming next with this next decade of atmospheric characterization that TESS and JWST combined are going to give us. And I just wish you, CFA, and MIT, your neighbor, great success in that endeavor, and I hope that we can be of help to share that expertise. Thank you very much.
Must be some questions.
Congratulations on the new release, that's great. So, if that reaction wheel number 2 didn't fail, next month we would have had 4 more years of data. And now with what you know about the pipeline and especially the noise from the stars, how many more statistics do you think we would have had?
I haven't done the calculation. I don't know what the...
Speculate?
Well, so you would be sensitive. I think the point is the geometric probability of transit takes a dive, right? As you go out in semi-major axis, it actually falls quite rapidly. So when we thought about what we wanted to do in the extended mission, it wasn't that we would get a lot of new planet candidates, although you would build up sensitivity and you push down to the lower signal-to-noise ratio. What we thought was tremendously valuable was the long baseline for doing the transit timing variations. So it was twofold. We would get some small number of planets, small planets in the habitable zone, but we would also have so many more planets to put in the mass radius diagram by way of transit timing variations. Planets that are interesting because they have, you have the opportunity to get the masses of planets that have low insolation fluxes. They're further away, whereas the Doppler method is challenged to get a Doppler signal when you have very large star-planet separations. So it's a unique capability, and we're working very hard to convince our European colleagues who are building Plato to do a bone stare instead of observing 1 year here, 1 year there. For that reason, in fact, I think to reobserve the Kepler field would have tremendous payoff. Their field of view is bigger than Kepler's, so they could overlap with it. I think that would be the best strategy for that reason.
The data release, is that going to include the images, the raw images?
The full frame images? Yes.
Yeah. So it'll be possible for somebody independent to come back and reanalyze the entire...
We don't have a full frame image every 30 minutes. It's a much lower cadence.
Okay.
Yeah. Not like TESS. TESS is going to have a full frame image, I think, for every cadence, for every long cadence, right? Is that correct?
But the original
Yeah.
pixels
Kepler
were,
did
of
not.
course.
What's that?
The original pixels, what was transmitted?
Yeah, the
around
target
over-
pixel files are there, but they're postage stamps, yeah.
So the data that you work with, that's all going to be available?
Oh, yes.
Okay. Sorry.
Yes, absolutely. We also have full frame images. So we didn't telemeter down every pixel at every cadence. We did postage stamps that we telemetered down.
In your period distribution plots, there was a small build-up just below 1 day. Is that a real physical thing? If you could. One of the ones near the beginning.
Like here?
Yeah, I guess so. There was a slight sort of bump in when you just have the histogram.
So when you go to periods below 1 day, you start to compete with other contact binaries who have, they can have a similar time scale. So the completeness, we have to tighten up some thresholds on our betting metrics in order to get rid of those signals, and so our completeness takes time. Also, the reliability is not as good for that same reason because you're competing with the other contact binaries. So I would caution you not to overinterpret that area.
Steve?
Yeah, I want to make sure I understand the bottom line. So you say more than one planet per star, and that's with a radius less than more than one rocky planet per star with an orbit radius less than a couple of AU? Is that?
So we're sensitive out to 700 days. Between 400 and 700 days, our sensitivity goes down
Okay.
quite a bit just because of the window function. The statistic of at least one per star is for all sizes and orbital periods. That number adds up to more than one.
So, and now if I think about only the gas giants, it looked like a lot less than one per
Yeah.
star. And what is, do you know that one number?
I don't have that number off the top of my head.
But
For the
somewhat.
hot Jupiter population, it's like 0.25%. It's very low.
0.25%.
Yeah, it's
Okay.
quarter of 1%. But that's so the hot Jupiter population seems to be correlated with the metallicity of the star population, and Kepler is looking in a part of the galaxy that has generally old populations, or we don't. The converse, I should say, we don't have any young stellar populations in our field, so we tend to have metal poor stars, and I think that explains why our population of hot Jupiters is significantly less.
But the average star has no gas giants. Is that a fair? At
Within
least
one AU.
Within one AU.
1 AU.
Okay.
Very few.
So before you all go, excuse me, give you your actual award. So the Myron Lecar Prize is hereby presented to Natalie Battaglia in recognition of exceptional contributions to the study of extrasolar planets and theoretical astrophysics. Thank you, Natalie.
Thank you very much, everyone.